Today we're going to look at a fun little optimization problem. Well, fun, but very reminiscent of some experiences that maybe you've had before in your life. If you've ever bought a new bed and tried to move a mattress around a corner in your house, you'll know that there are certain places that don't want to go. So this is kind of like a mathematically idealized version of this problem. You've got a house, you've got a corridor with a width of 3 meters one way, and around the corner it's 2 meters. And the question is kind of, what's the longest solid straight object that we can move around that corner without it getting jammed up? But we're just going to pretend that the thing we're trying to move, just to make life a little bit easier, is just a straight line. So for example, if our thing was this long, I'll just draw on a wee object, here we go, then you can kind of see that that probably wouldn't, if that was solid, I probably couldn't continue on around the corner because it would kind of be stuck in that position. So our problem is to find out what the longest thing is that we could actually get around this corner. Now the way to understand this is, if you just imagine the situation for a second, the longest thing as it goes around is always going to be basically hung up on this particular corner. So it's going to be stuck there as it goes around. And so that you'll be stuck on this corner and the ends will slide along the walls and then you'll be free to move once you're around. So if you imagine kind of just drawing lines through that point, here's another one. And this is kind of imagining the progression around the corner. We'll draw another one here. It's going to be something like that. As we go around this corner, you can see that these lines are going to kind of change their length. And that's going to be stuck to that point, so it's going to be way out, kind of out here. So it's going to be sort of moving from a longer line, a bit shorter again, a bit shorter again, and then as we go round, they start getting longer again. And so it kind of stands to reason, if you think about it for a minute, that the longest possible item that can actually get round the corner safely will be the shortest version of this line as we go around the corner. Sorry, it's that one there, isn't it? So really the way we can find this is by solving an optimization problem to find the shortest line that's constructed in this way. So let's just delete some of these lines and just get a single one, just to make this a little bit easier to visualize. So let's just draw one of these on. So basically the constraint with this line is that it goes through the corner and that it meets the two walls. And we want to know how long the line is. And then once we've done that, we want to minimize it. So normally when we're solving an optimization problem, we want some kind of parameter to minimize over. And there are a few possibilities. You could set it up maybe as the position along the wall. Down there, we could call that X or something. That might work, but probably the most natural one to use for this problem would be instead the angle that is at to the corner. So probably the easiest thing to do here is have this angle here, theta, be our parameter. So as we vary theta, that gives us all the different lines that are of the right format. And that's also going to appear down here as well. And so basically we want the length of this blue line as we change the angle theta. So let's split the length of the line up into two pieces. We'll call this one L1 and this one L2, and then our overall length is just going to be the sum of those. Okay, so let's see how we can figure those out. Well, we just have two right-angled triangles here. So really what we have is a right-angled triangle with a side of 2 and a right-angled triangle with a side of 3. And so we can just do a couple of basic trig expressions just to work out what those two pieces are. So L1, well, we're going to have cosine of theta is equal to 3 over L1. So L1 will just be 3 over cosine of theta. And then cosine theta is also going to be equal to, well, not cosine this time, sine theta will be 2 over L2. And so this is going to be 2 over sine theta. So now we have our length L as a function of our angle theta, and we should be able to then find the minimum value, and hopefully just by the sort of sketch we did before, you'd be satisfied without having to do any further tests that this is actually going to be a minimum. We should be able to find the minimum by just differentiating with respect to theta and finding out where that equals 0. So minimum should be where dl by d theta is equal to 0. All right, so now all we have to do is basically differentiate this and see what happens. So let's see. I'm just going to rewrite my equation here. So L is 3 over cosine theta plus 2 over sine theta. I'm going to need its derivative, so dl by d theta are going to be a couple of chain rules. So 1 over something goes to negative 1 over something squared. So that's going to be negative 3 over cosine squared theta times the derivative of cosine theta, which is sine theta, just by the chain rule, is, sorry, negative sine theta. So that will also have the effect of removing that negative sign. Plus, let's see, it's going to be derivative of 2 over sine theta is going to be negative 2 over sine squared theta, all times the derivative of sine, which is cosine theta. All right, and we want this equal to 0. So we can also write this derivative as a single fraction, and that will be, so it's going to be cosine squared times sine squared on the bottom. So that will be 3, need to multiply the first bit by sine squared, so 3 sine cubed theta minus 2 cosine cubed theta, just multiplying that second fraction top and bottom by cosine squared. So we've got a common denominator of cosine squared theta sine squared theta. All right, so that's nice. And we can see that so long as theta is not 0 or 90 degrees, that the bottom of that fraction is going to be positive. And hopefully just from the geometry of the problem, you can see that we're not going to end up in those extreme 0 degree or 90 degree situations for our minimum. So we can probably safely not worry about that denominator causing any trouble. Right, so what we want to do is we want to set that equal to 0. So dl d theta equals 0. That implies that now, when we've got a fraction equals 0, we only really need to look at the top row. So long as we're confident not going to be any weird things going on with the bottom. That just implies that the numerator of the top of the fraction is going to be equal to 0. So we can ignore the bottom part. 3 sine cubed theta minus 2 cosine cubed theta equals 0. What on earth are we going to do with this? Well, the thing that I'm remembering here is that tan theta, just a little, when you've got sine and cosine, just remember the definition of tan is sine theta over cosine theta. So I can make this thing in terms of tan theta by just dividing by the cosine term, which becomes, so if I divide everything through by cosine theta, it's going to be 3 sine cubed theta over cosine cubed theta minus 2 equals 0. And so this piece, that there is just going to be tan cubed. So what we end up with, if we just do a couple more steps of rearranging, is we get tan cubed theta is equal to, well, the 2 is going to come on the other side, and we're going to have divided by 3. And so we're almost there. So that means that tan theta is going to therefore be the cubed root of 2/3, which means that our angle theta is going to be the inverse tan of the cube root of 2/3. Okay, so that's all kind of annoying, but at least it's a thing we can do. And don't forget the thing where we're actually asked for the longest length. So once we've got this value of theta, we then go back to our expression for the length, which was up here, and then we'll just plug in our value of theta. So I'm going to do that on a calculator, but basically maybe before we do, just have a look at it and see if you can fix in your head what you think that value should be, just based on the geometry of that problem. So you can see whether our answer seems reasonable once we come up with it. Okay, so we've got our expression for theta, which is inverse tan of the cube root of 2/3. So now I'm just going to jump into the computer and I am going to see what that is. Right, so once again I'm going to use a computer to do this. So I have that theta is the inverse tan, which is often a tan in computer programming languages, of the cubed root. Remember, cubed root is power of a third of 2/3. So it's going to be 2/3 all to the power of 1/3. It's going to be my angle theta, and that of course will be in radians because that's how the world works. And then our expression for the length, that was just equal to 3 over cosine theta plus 2 over sine theta. And hopefully that will give us a number that sort of fits in with our problem. Let's have a look. Tells me that my length L is 7.0234. Okay, so hopefully you're reasonably happy that that's going to be a minimum just from the argument from before, but maybe if you just wanted to be sure, we could try some values of theta on either side of it. So let's go for, so what was theta was 0.718, so let's go for maybe 0.712 to be a little bit on to the left, and see if hopefully this number is a little bit bigger. It is at the 4th decimal place, 7.0238 versus 4. And then let's just put theta a little bit larger, just again to satisfy ourselves that we have indeed got, we can have 725, have indeed got a minimum. And this hopefully again should be a little bit larger than our solution value. And then, once again it is. Okay, so let's just switch back to the iPad real quick. And we will just summarize those results. This gave us was equal to 7.02 meters approximately, rounded. And if you look at the picture, I don't know about you, but for me that was slightly surprising. I thought that the answer was going to be slightly shorter than that, but that is indeed the longest stick or piece of furniture that you could get around that corner. And of course, if you are moving house and you're doing it with a mattress, don't forget the easy answer is to turn it on its end, then it's way easier to get around. Cool, that's enough for now. We'll see you next time.